SwayamPrabha. Digital India. Educated India.
In the last class, we learned that phase Doppler particle analyzer or phase Doppler velocimetry technique can provide us measurement of the particle size as well as particle velocity. It is possible to even achieve measurement of 3-component velocity along with particle size, okay, which is a measure advantage in PDPA compared to LDV, which can only give us particle velocity. Now the question is, how do we apply PDPA for two-phase measurements? So although this technique is primarily designed for the dispersed phase, it can also be applied to the carrier phase or the continuous phase. How? Now what do we mean by two-phase measurement? This means that apart from the particle phase, we should be able to measure the carrier phase as well. And how we can do that? By introducing proper seeding in the flow and through signal discrimination, that is by sorting out the signals due to the seeding particles. So by that way we can, and the seeding particles basically refer to velocity of the carrier phase. So by this way we can measure two phases. So this is what is given here. So first we seed the carrier phase gas or liquid with fine tracer particles. Then we get, or the PDPA detects the Doppler burst from both tracers and dispersed particles, and then we filter out. And now we have the advantage that we know the particle size. So we know which one is seeding particle, which one is inertial particle. So with this we can obtain several statistics of the two-phase flow, including the particle phase statistics, and this we can get conditional on particle size. So what does this mean? This means that we can measure the particle phase property based on the particle size. For example, particle velocity itself. So if you use LDV, it will give you the velocity of the particle over a time. Okay, let's say you run it for 1 second, say 10 seconds, then over that time it will give you what is the particle velocity. However, it won't be able to distinguish which particle size corresponds to that velocity. Or in other words, if you use LDV, it will only give you average velocity of the particle, where averaging is not only with respect to time but also with respect to particle size. It is blind to the particle size. However, now we can segregate the particles according to the size. We can bin them because we know the particle size. Let's say 5 to 20 micron particles, 10 to 25 micron particles. Let's say we bin them, and now we calculate the average size. So now we know for this size class what is the particle velocity, and this is a big advantage, because by that way we will be able to know particle size velocity correlation. And then it can also provide the carrier phase statistics at the same location, at the same point, if we introduce seeding particles. And by that way we can get the mean slip velocity. Mean slip velocity means slip velocity which is averaged over time. So mean droplet velocity minus mean gas velocity, or mean particle velocity minus mean carrier phase velocity, that is the slip velocity. And importantly, we can get that also conditional on particle size or based on particle size. For a given particle size class, we know particle velocity, we know particle carrier phase slip velocity. So we will see this through an example. Here I am showing these results from this paper by Ferrand et al. So here they have considered a jet, an air jet loaded with fine droplets. as you can see, this is the experimental setup. This is the nozzle. There are 3 injectors, you can say, which are placed here, and the atomization is achieved here, and the air carrying small droplets comes out of this injector. So this is the experimental setup, and they performed PDPA experiments at different axial locations as well as different radial locations at each axial location. So basically they scan through the flow, and they see polydispersed particles over a wide range, as you can see here, from about less than 5 micron to about 120 micron. So this is the particle size distribution that they could measure. Now, they could also calculate the Stokes number based on the particle size class. As you can see here, they have considered different size class of particles like this. Okay, and they calculate the Stokes number as the ratio of particle relaxation time to time scale of the flow, where time scale of the flow, how do we get the time scale of the flow? So in this case, what they have done, although I haven't shown here, so they measure the carrier phase velocity. How? By assuming that these small particles are flow tracers. Okay. So basically, at any location, you take the PDPA measurement over some long period of time. Okay. And then you segregate the data based on the particle size, and then you calculate the velocity of each size class. Okay. So for example, 0 to 5 micron particles, you collect. So because PDPA is a single particle counter technique, so at any instant of time, you know, okay, this is the particle size, this is the particle velocity. So for 0 to 5 micron particles, they have collection of velocity measured at the same point. So if you take the mean, that gives you the mean velocity. If you take the standard deviation, that gives you the turbulent fluctuations. So that is how they calculated this U dash. And also they have the mean flow. So mean flow in this case, in the case of this jet, the mean flow will be, say, somewhat like this. Okay. So this is the velocity of the gas. Okay. Now they calculated the jet half width. What is jet half width? This is the radial location at which, this is called R half. This is the radial location at which the value at the center becomes half of this. So this is U naught by 2. So this location is called jet half width. So they assumed that the large scale eddies, or it has been also shown, it is well known that the large scale eddies are of similar order. So this R half provides the length scale of the large scale eddies. So we can take this ratio R half divided by U dash, and this will give time scale of the large scale eddies, or this will give the eddy turnover time. So that's what they use in Stokes number. So basically the Stokes number that you see here refer to Stokes number based on large scale eddies. And now what is interesting here is that you see that the Stokes number obviously increases with particle size. So this one corresponds to this, and the largest size class corresponds to this, as expected. As you increase Stokes number, as you increase particle size, Stokes number will increase. But also the Stokes number reduces as you move downstream. So what does this mean? This means that the particles tend to follow the fluid in a better way as they move away from the injector. Okay. And this is happening because the large eddy time scale is actually getting longer. So, away from the injector exit, the flow becomes slower. As the flow is slower, the time scale of the flow is longer. This is the reason why Stokes number reduces for all cases. But you see that close to the injector exit, the Stokes number can also be 100, and this is Stokes number based on large scale eddies. This means that close to the injector, the droplets are just unresponsive to the turbulent flow fluctuations. Okay. So, you see how much information we can obtain by only by measuring the particle size and particle velocity. Now, similarly, they have measured the mass concentration. In yesterday's class, I have discussed that PDPA can measure mass concentration. Now, what is mass concentration? How much mass is contained in unit volume locally. Okay. And this mass concentration can also be measured conditional on particle size class. Okay. So, this plot shows at a given or at a representative axial location radially how the mass flux changes. And here you see this is the mass flux for the small particles. Okay. So, it is almost negligible. Okay. While the mass flux increases in this case with the particle size. This is not mass flux, sorry, this is mass concentration. That is, you see the unit. Okay. So, and yes, and in this case, when they calculated the Stokes number for very small particles, as you can see here, this is smaller than -1. If you leave this part, see, they have assumed that the 0 to 5 micron particles are tracer particles, but still you see here the difference, that close to the injector exit, even the small particles have higher Stokes number. Higher means it is of the order of 0.1. It is not much less than 0.1, which is the criteria for them to be tracer particles. So, they are actually tracer particles when you are, let us say, somewhere here after this. Okay. And they have done the later analysis. So, later they have measured, as I will show, the correlation between the particle and the fluid velocity fluctuations, and that was done away from the injector exit. So, this slide shows the mean gas velocity vector plots for the case when they do not have particles and when they have particles. So, they have also done experiments without introducing the spray. This is only air jet. So, the profile, if you see, so each of this is one experiment. Each of this that you see. So, you can imagine the number of experiments they have done. Okay. So, they have radially scanned through the flow. Okay. By either you can move the injector or you can shift the PDPA setup. Okay. Nowadays, advanced systems with very good traverse, with very high resolution is available. Of course, the cost is high, but you can take measurements with very high spatial resolution. But you have to keep in mind that these are all statistical quantities. You cannot get this kind of profile which is instantaneous. That is, at one instant of time, you cannot measure the particle velocity or the fluid velocity at different location. These are statistics, means mean, standard deviation, these things you can calculate and show. So, if you see closely, you can see that in fact the carrier phase velocity is influenced by the particle. So here, for example, you compare, the profile looks similar, but the magnitude are different. The velocity gradients are different because of the presence of particles. So this one shows a very good example. So here you can see how the velocity gradient has changed. So once the mean velocity gradient changes, this means that the mechanism of the turbulence modulation, okay, is coming into picture, or the turbulence will be modified, because turbulence gets energy from the gradient of the mean profile. And here you see that it has changed because of the particle. So this means that the turbulence spectrum will also change. And this slide shows how the mean gas velocity and the turbulent kinetic energy varies along the center line of the jet, only, with and without particles. So for example here, you can note here that they are plotting the inverse of the mean gas velocity, So you see that in both cases, this parameter increases, which means that, and u naught is the velocity at the exit, velocity of the flow at the exit of the injector. Okay. So this increases, this means that this value of u, that is the mean gas velocity, actually reduces as you move away from the injector, which is expected. However, you see the difference. So this is going down, means actually the mean velocity in the presence of particle is increasing. Okay. Now similarly you see the turbulent kinetic energy. So this is normalized turbulent kinetic energy, and you see that the turbulent kinetic energy everywhere it is reducing. So the turbulence is being dampened everywhere here because of the presence of the particles. Now next question, as we posed this question earlier in the case of LDV, is it possible to measure both the carrier phase and the dispersed phase simultaneously, which means at the same time, is it possible? The answer is no. Why not? Again, because it's a single particle counter technique. You measure only one particle in your probe volume, that can be either tracer particle or inertial particle, but you cannot measure them both. But these researchers, what they did is that they introduced an interpolation technique to measure the gas velocity seen by the droplets. Means, what is the velocity that a droplet sees? What is the gas velocity that a droplet observes? Okay. So this is closely related to the point particle assumption that we have discussed earlier. So in numerical models, they use point particle assumption. What does this mean? This means that you account for the effect of particles, but you don't assume that, but you don't consider that the particle is actually present. For instance, you can model the drag force using Stokes drag model with some correction factor, but you won't be able to calculate the boundary layer around the particle, because you are assuming that the particle is physically not present. This is what is point particle assumption. So in point particle assumption, this kind of terms comes in the model equations. We have discussed this earlier. Now if you want to model this term, you have to be able to find them, or you have to be able to measure them if you want to validate your models. So this means that at the same instant of time and at the same location, we want to know what is the fluctuation in the particle velocity, what is the fluctuation in the carrier phase velocity. So here you see these triangles actually represent the droplets that they have measured with time. So, you see that it is not continuous. Obviously, it is not continuous. The droplets won't come continuously through your probe volume. Similarly, seeding particles also. But because usually the seeding particle number density is high, so you see more of this. So, these dotted lines you see this. These are the seeding particles. Now, what we want is that what is the velocity of the gas phase seen by the droplet, means this velocity, which you do not have. You have this value and this value, but you do not have this value. So, this corresponds to the time at which you measure the droplet. I hope you are able to get it. So, basically you have discrete data. Okay. Now, at some point you have measured a droplet. Now, you want to know at that time what is the gas velocity, which you cannot measure. So, basically you interpolate considering the neighboring values, and that is what they have done. So, you see, for example, this is the gas velocity seen by the droplet. Okay. However, the problem is that the uncertainty remains because it depends on the scheme of interpolation. How do you know which interpolation scheme gives you the correct result? Because there is no other way you can validate this. Okay. However, they have used this approach to measure the velocity correlation that I will show. But here again I would like to mention that in this case they did not use any seeding particles. Okay, I did not explicitly mention this. So, okay, if you remember the droplet size distribution. So, the size distribution itself is such that they have large number of small particles, which are 0 to 5 micron particles. So, they treated these as tracer particles, they did not have to separately introduce. And when they calculated the Stokes number of this away from the injector exit, it satisfied the condition. So, that is why these are tracer particles. So, this is another way of two-phase measurements without as such introducing or adding seeding particles. And here are some of the results that shows these correlations between droplet and gas phase in this case, or particle and fluid phase. So, they have measured it at different radial locations, and what is important is that again you can do this based on your particle size. So, that is the power of the technique. Okay. And they have done further analysis. So, basically here they are measuring both U component as well as the V component. So, you can calculate the correlations with different combinations, okay, and that is what they are showing, and they have done a very detailed analysis. You can refer to this paper. Okay. So, the whole idea of presenting this was to give you a flavor of how the techniques are used to extract the physics behind the two-phase interaction process, and how these techniques can give us very, very valuable information. So, these data are really valuable because they provide a platform to validate numerical models. Okay. So, finally, to summarize, whatever we have discussed in the online measurement techniques, they fall under the single particle counter category. So, basically here what is shown here is how can we do two-phase measurements, that is how do we measure the carrier phase. It can be done two ways, by either by adding seeding particles or by selecting particles which already exist, which can be treated as seeders. And once the data is, you collect the data, then we can do some processing to filter out, and with PDPA we have the advantage of the information on the particle size, so you can segregate them well. So the crosstalk reduces to a great extent because we know the particle size data. However, the problem remains with both approaches. So this is the approach where you consider some of the particles in your flow itself as tracers. Now the problem with that approach is the validity of the tracer assumption. So this you have to validate, you have to kind of validate that the Stokes number is actually low. Second thing, low sampling rate of the tracers. So in this example that we have seen, 5 to 10 micron droplets or 0 to 5 micron droplets were present sufficiently. That is the reason why they could do statistical analysis. But if the number of such particles are low, you won't get statistical convergence. So in experiments, while we measure statistics, it is very important to ensure that statistical convergence is reached. So it is like this. So let's say you want to find the velocity of the carrier phase. So you measure the tracer particles, first tracer particle say V1, then V2, V3 and go on, and you go on doing that. And then to calculate the mean velocity, you basically add them up and divide by the total number of samples. So this is the mean. However, you have to make sure that statistical convergence has reached, which means that now let's say you collected 10,000 samples. Okay. Now if I throw out 2,000 samples and if I make it 8,000 samples, are you getting the same value of the mean within statistical uncertainty? So you have to ensure that this state is reached. So how we do this is that you consider the number of samples and you go on plotting the value of the mean velocity that you get in this example. So let's say you get a trend like this. So this shows that after certain number of samples, the value does not change much. So then you stop here and you say that, okay, you need this much samples to achieve statistical convergence. Now, if you have less number of tracer particles, or for that matter, less number of particles of any size class, then this you may have large uncertainty in the measured statistics. Okay. Or else you will have to take the measurements for a very long time. Okay. This is also a problem when we measure large droplets. Usually the probability or the number of larger particles are low. So if you want to find some statistics for the larger particles, then the number has to be high, which means that you have to run the experiment for a longer duration. However, that itself might be a challenge in some cases, because it is difficult to maintain the same condition for a longer duration. Planar or volume imaging technique, which are also called whole field measurement technique. So from point measurements to volumetric measurement or planar measurement. Planar measurement means you take measurement in one plane. Volumetric measurements means you take measurement in one volume. So you imagine you get the velocity in one plane at all points in one plane, or at different points within a volume. This is in contrast to, for example, LDV, which can give you the velocity at one point only. Whole field measurements are in contrast to point measurements in the sense that in this case we avoid multiple measurements. You don't have to take so many measurements or you don't have to scan your probe throughout the measurement location. Importantly, we can get 2-point statistics. Mainly this is relevant for turbulence measurement. 2-point statistics means if you take measurement at 2 points, 2 different points simultaneously, how do the data correlate to each other? That is what is 2-point statistics. Inherently, we can visualize the particle distribution because these are imaging based techniques. We can actually see how the particles are distributed, which is not possible in the case of single particle technique instantaneously. But still, PDPA can give you, for instance, the average number density or average volume fraction or mass concentration as I have shown. So if you go on measuring throughout your flow, you can get a map or you can plot a contour of the mean concentration. However, instantaneously you won't be able to know. So that is the reason why unsteady phenomena such as particle clustering can be studied. The phenomena which are dynamic in nature, particle clustering for example, at any instant of time you have clusters of particles formed which will disappear after some time at the same location. It may disappear. Okay. And if you take average measurements, you won't be able to see these instantaneous features. But using planar or volume imaging techniques, we can achieve those. So that's the advantage. So in this context, particle image velocimetry or PIV technique is well suited for whole field measurements, and we will discuss this first. Then laser induced fluorescence or LIF based PIV techniques are also useful for in this context, that we can measure simultaneously the 2 phases. There are other planar techniques like eyelids, PDS, which can also provide measurement of particles in one plane. Now we start with particle image velocimetry technique. So what is particle image velocimetry technique? Is that, as the name suggests, here we image particles. So this is a whole field or planar measurement technique. This is a two-step process involved here. So basically, as you can see here, we add some seeding particles, as in the case of LDV in the flow. We illuminate the flow with a laser sheet so that we can visualize the particles. And then by capturing 2 instantaneous images separated by a very short time duration, we can capture the movement of the particle in the 2 frames. And then by doing cross correlation of the image pattern, we can find the velocity of group of particles. So 2 things here. Similar to LDV, here we don't measure fluid velocity, we measure velocity of seeding particles. Second thing, we don't measure individual particle velocity, we measure velocity of group of particles. Okay, so this is the basic principle of the PIV technique. Then, so this is an example that I always show to understand the concept behind PIV, though this is not strictly a PIV image. So here you have a flow, you have a video of flow behind a circular cylinder. The flow is seeded with small particles, and this is illuminated with a laser sheet. So if I stop at any instant, here you can see the traces of particles. You don't see particles, rather the traces of the particle. But somewhere here you see the particles, and somewhere here and here. But in the main flow, you see particle traces or streaks of the particle. This is the reason why this is not a PIV image, because in a PIV image, you have to see individual particles, not their streaks. Okay. But here this tells us that this image itself tells us that the flow time scale is much longer here and here compared to the bulk liquid. Why? So when we are, so obviously we are observing this through a camera, and there is a shutter in the camera. So the shutter opens and we record, and then the shutter closes. Now what happens, because the recording time or shutter speed is low, that is the reason the time over which we capture the image is longer than the time that a particle takes to flow. That is the reason why we see the streak of the particle. For instance, if you take your mobile camera and take a photograph, let's say of this pen, and I am waving this pen, you won't be able to see you won't be able to get a crisp image of the pen. Rather, you will see a streak. And this is happening why? Because the shutter speed is low, or the camera exposure time is longer than the time scale over which you are waving this. So exactly same thing is happening. But then why do we see particles here? This is because here the time scale of the flow is low, because this is in the wake region. Here, because of the boundary layer, the flow velocity has gone down. Whatever is the flow velocity in the bulk fluid, if you have, it can be even supersonic flow. Still, if you have wall, the flow velocity there will be close to zero. Means on the wall it is zero, and in the vicinity of the wall it will be some small value. And this is the reason why you are able to see the particles. Okay. So the point is, this has to be ensured in the PIV image that you actually capture a frozen flow field. Frozen flow field means the particles are almost not moving. Only then you will get the correct image of the particles.